what it is, why it's interesting, kind of why you care, and then a quick demo. I think I can, show a PowerPoint and kind of give an overview, but it's always a bit more interesting to see it done live. So we'll spend some time doing that as well. Cool. So yeah, just to kind of get started, want to give a quick introduction to Databricks Delta, kind of, what it is and why, any of us should care. So kind of just, jumping into it, Databricks Delta Lake is an open source file format, which is a big focus that Databricks has on openness of this. But it's an improvement on top of kind of standard, open source Parquet files, where they've kind of taken a Parquet file and added some enhancements to it to, provide better support for transactions, better support for kind of handling metadata, kind of what's going on at the table, schemas, things of the sort, and also for handling, multiple data velocities, batch streaming, simultaneous use as a source data set and a sync if you're in a streaming use case. Where a lot of that is still, built on kind of standard Parquet. So, the data should be somewhat familiar if you've worked in that with kind of a bit of enhancements on top of that. So, one of the key features that kind of comes with this is a transaction log, which, if you look at a structure of some Parquet data versus you look at a structure of some Delta data, you'll see that this is kind of an addition here where the transaction log, is kind of a series of, files that track all the operations that you're doing on your table, inserts, updates, deletes, optimizations, it keeps this history of your data, of your table, of all the operations you've done. So you kind of have this, history of your data, which, can kind of allow you to go back and audit it and use it as really a single source of truth of what your data is and kind of how that should work. And in doing that, it enables the tables to be, ACID compliant, which we'll get into a bit more in a second. And as I said before, you can combine streaming and batch jobs into the same table at the same time, kind of in the same workflows. If you have a, batch process that catches up on stuff, that works for that. If you have streaming that's kind of writing into it, that works as well. And, if something's, if I'm a, data engineer and I'm writing a streaming job into a table and you're a, a data analyst and you want to look at some of this data coming out, these are, handled and set up such that, we could be doing this work at the same time and we'll see the, most updated version of the data and we'll all kind of have our process be isolated together. They'll still work. So going into kind of some of the key features, the big one that they will mention is the, kind of ACID compliance. It has this full support for concurrent reads, writes, batch, streaming, isolation. So, going into all this, the start is the atomicity. So, each operation that you have on the table is, broken into a, kind of one commit, and it will either, fully succeed or fully fail. So if you get about halfway through writing your data and, you have, a few new files written out, but then something happens and it fails, there's no new information written into the transaction log, and kind of by virtue of that, then you can see that essentially that operation never happened. So it kind of gives you the fully rollback. If you go and query the data after it, it'll be just what it was when you started. So it, the data won't change if something fails. So I've personally had the experience of having some corrupted things written into a Parquet file that happened halfway through, and it was not a fun experience. So I think this is a big improvement on that. The second part is the consistency. So any actions that you can do, take your data from a valid state to another valid state. It can't go to an invalid state. It won't allow you to kind of perform some operations that are going to corrupt things. That's not to say that there's nothing that can go wrong with your data. There's certainly the level of mistakes that any of us can make as a developer, but it won't kind of corrupt your data, and your data will still be it'll still be a functioning table. You may have to roll back a few changes and correct it from the business side of things, but not from the not from the kind of function side. The I is isolation. It's the tables ensure that the concurrent commits will have the same outcome as running them all sequentially. So you can have multiple people working on the same data at the same time. You can kind of line things up that will kind of essentially work as if they're sequenced. It can do things concurrent if they're working on different parts of data. It'll prioritize order if they are working on the same data. So but the processes will kind of run through, and they won't interact with each other at the same time. So that should all be separate. So you can have multiple people working on the same data at once without kind of a ton of risk. And the last is just durability. Once a transaction is committed, it's it's there in the transaction log in the history. It'll stay in there regardless of the system failure. Commonly this is being written out as some object store. We as 3Cloud use a lot of Azure, so data lake storage, blob storage. If you are someone who uses AWS, S3 most likely. And I don't know the corresponding one for GCP, but the same type of low cost storage. It'll remain there, and it'll kind of exist there until you get rid of your data. So just some other features as well on this. They've added kind of insert, update, delete support into Deltas. Parquets you can append, but you're just adding new files in this. You can easily update existing records. You can delete specific records. You have kind of a lot of fine-grained controls on what you can and can't do, and similar, just like a kind of SQL upsert, if that's a familiar operation where you can update records if they match a join condition, and if not, insert, if not, do something else. But you have that kind of fine-grained control where you can interact with individual records that have already been written into the table pretty easily. The next one, which is one of the ones that I've personally taken advantage of a lot, the time travel and history. So in that transaction log, you get all the operations, all the successful commits that you've done to your data. So if you are developing something and you realize, oh, I've made a mistake, I've got my logic wrong, but it was right at this step 5 operations ago, you can just kind of back out to that previous version, restore your data, and go from there. You can also use this for audit checks. If you want to see what's been going on through there, you can see the whole history, who's done what operations. There's schema checking, which I touched on, I mentioned a bit briefly, that allows some enforcement on data quality. So if your table kind of changes over time, the kind of default behavior of a Delta table will be such that the schema, the code will fail unless the schemas match up. So you can make sure that nothing's happening that you don't expect it to. And if you are writing something in, if your upstream data has changed, you'll get an error, so you can check it out. It'll make that check and validate before something could get written in and happen incorrectly. And you can also override that if you want to. If that's a known thing, you can. There's just an easy option to kind of override that behavior. So if the schema change is expected, then you are good to go. The Delta cache is another kind of one of the optimizations that Databricks has made. They have some since everything is lazy evaluated and goes back to the source. One of the Delta cache will do is it'll make some copies automatically separate from the normal Spark cache to local disk for kind of quick reads from there without taking up the memory. This actually works on Parquet and Delta. It's just kind of a feature of Databricks as well. And the last is Databricks is focused on openness. It's built on top of Parquet files. They've open sourced the entire project, and it's they're adding a number of kind of connectors that you can interact with Delta from. When I think I first started working with Delta, you wouldn't be able to use it from Python, but now there are ways where you can just kind of call it from a standard single threaded Python application and read some of that data out. and also with some of the updates they're making with Delta sharing that they announced in their summit a couple months ago now. You can also share sections of the data with pretty fine grained control, and share those out to whoever else. Just a quick comparison of Delta and Parquet, since they are somewhat similar. They're both open source. Open source. Parquet, the standard file for Spark, able to be read by other languages. Pretty easily if you want to connect to Presto, things like that, other things to query it. It's a pretty standard format. Databricks, it's open source. It works best with Spark. They are adding on more things. So, I called Presto and I had a use case a while back where I had Presto data that, we were using Presto to query and we weren't really able to query it through query Delta data. So we had to use Parquets, but that's something that's been changed relatively recently. I can go there. So similarly, kind of go down, with Parquet and data Delta, there's the difference in the writes, which I think is a pretty big operation for Delta. Parquet files writes can fail midway. They're not reversible. You can kind of get into, kind of pretty nasty situations of half written data. With Delta, each operation, because of the atomicity of it, it'll fully succeed or will fully fail. And if it fully fails, then you're good to go. It's not, nothing's written. Same thing with the schema enforcement. Parquet, schemas should be consistent within the partitions, but not necessarily across. So you can get kind of some weird behavior if you're loading across that. Where in Delta, the schemas are enforced to be consistent across the table. And then again, Parquet has pretty, already comes from a place having pretty good, push down filtering, columnar storage, so you can really select only the columns you want, have that really save up a lot of time. So you have great ways to kind of reduce the amount of data that you're loading if you're loading in from a big data where you don't need everything. Delta has that as well, so it's built on top of this, and they've taken it a few steps further with, the way they, kind of have the stats collection on some of this, data pruning and the optimizations that you can make to a table for, kind of co-location of data, compression of files. Compression is probably the wrong word, but combining files into optimal file sizes, so you don't end up with a bunch of small files or files that are too big. So they can make tuning of kind of all the files very, very pretty simple. So that's a quick intro, and then this fits into Databricks' Lakehouse, which is kind of their common architecture that they are recommending now, and it kind of fits in as the backbone. So if you kind of consider the Lakehouse, the Lakehouse is designed to be the kind of best of both worlds for a data lake and a data warehouse. Data lake where you can have any type of data, you store it on low kind of cheap hardware. And it can be scaled out infinitely on Azure AWS kind of service like that. It's good for machine learning. You can have kind of all this raw unstructured data that data engineers, data scientists can make what they will, but it's not always the best for BI, and also can kind of turn into a nightmare if you're not really careful about how it's organized, how all the processes go. And so, they've taken kind of the good parts of that, all kinds of data, good for machine learning scale, and taken some of the things from a, traditional, data warehouse, the concurrent querying, optimized for those queries, the kind of, better controls for BI, and they've added the transaction support, scheme enforcement. As I said, you can have all these different types of, workloads, data types, streaming batch, and you can support a number of different things, all kind of from this one type of data with, Delta as like the standard storage format to be put into that. You can do data engineering easily on a Delta table with Spark. You can stream in and out. You can do machine learning, from the cleaned up data, or kind of different levels of data, depending on how you have your architecture set up. And you can do, once you have it cleaned up, it's it's well structured, well optimized, and easy to query in BI through a number of different platforms. So this is kind of a the architecture that Databricks will like to push and kind of is becoming a bit more popular. And to kind of implement this well, Delta is kind of what they've designed as the backbone for this with the way the kind of data will be stored. So, I gave, a really quick overview. If there's any questions, just put them in the sidebar and I'll try and get to them. But, I think more interesting than just kind of talking about this is just kind of a, quick demo on all this, kind of showing, what's there and just kind of walking through some of these features, seeing how they work, seeing what the data looks like, and seeing, kind of that it can be, relatively simple to get started. So set this up on a Databricks workspace that I have, and there's two notebooks, a demo one and a setup one. So I've already run the setup one, that takes a second. But just to give some context, just kind of wanted to run through a simple data engineering use case with this, where you can kind of see, read some data from a different format, write it as a Delta, go through the features of Delta, do some corrections. So I'm running this on a small cluster because I, don't want to spend a ton of money, and I'm taking a subset of the New York taxi data. I think I've taken the green taxi data because there's fewer of those, and there's it's a bit smaller. But this is a data set that if you have a Databricks workspace, it comes in the Databricks' kind of their Databricks data sets folder on DBFS. There's a number of other things there. But I've just kind of picked this one. I've played around with this one before. So in the setup one, I'm just saving, kind of importing some data, subsetting it down and saving as a Parquet. So we'll kind of pick up from there, where we have a few different months of taxi rides saved as Parquet. And we can just kind of check those out to see what's there. I've set an input path, and you can see, I'm looking at, green taxis for a few different months: November of 2013, December of 2013, and December of 2019. Those are the kind of top level Parquet folders. And then, we can look at one of those and see that, in these folders, we have all the, parts of the Parquets and, written out across a few different files. So this is kind of where we're starting from. The other folders will be, relatively similar, but just kind of coming from a kind of smaller data set where we can, kind of start this. It could be anything in your use case, but just kind of, this is an easy place to start. So just to kind of really get this started, just want to read this data in and understand what's there. We can run the display, we can see that, we can do some visualizations with the display as well if we want to. But just kind of running through this, we have kind of the fields that would describe any taxi ride that you may take, the pickup, the drop-off time, where it happened. Right now they have it in Latin longs, the passenger distance, fare, some taxes and fees they put on cabs, the buttons they press when you get in, you have no idea what it's for, tolls, and the total. And then I've added a date column. So there's a, timestamp for when it is. But for demonstration's sake, I want to partition this data out by the date that it started. So I'm taking the date, the timestamp column, and I'm just kind of casting off the minutes and seconds part. So we just have the date, and then when I write it out, I'll use that to partition the data. So kind of standard for a use case. We can then only load specific partitions. We can kind of have that just to, speed this up a little bit. But, from this, I'm not going to do anything too crazy to this. I just want to write it out, get something started as a Delta table. So from here, I'm just writing this data frame out. It's, the overwrite mode. You can have overwrite or appends. I have the format as a Delta. I'm partitioning by the date column that I created, and I am writing it out to, a path that I've kind of pre-saved as a variable at a time. So that'll run out. It'll write the data out to the location there, and then we can just kind of check out what that ends up looking like. give it a second. It's, creating the, first version, version 0, the snapshot there. When we look at kind of the data stored in here, we see a number of directories. The first one is for the Delta log, which is that transaction log that I mentioned that, kind of keeps the record of all the, commits and, other options there, and then or other operations there, and then we have all of the folders for the different partitions. So, this will be the folder for, kind of each of these dates, as it were. So you can go into, just pick one of these dates, and we can see that there's a few files written out into here, that these would be, all the rides from November 1st of 2013. So I mentioned the kind of transaction log there. We can look into this file as well and see this. They in the folder here, we have our Delta log folder, and then each commit will be kind of sequenced with the JSON file. So you can go in here and we can look at what's been done. So this isn't the prettiest of outputs, but bear with me. But you can see, some general info on the commit. The timestamp, when it was made, the user ID and the username, me, the operation, and some details about the operations. You can see it was partitioned by this, the notebook that ran it. So, if you wanted to track this back to the notebook in the cluster, you could see that. And then it has some information on the file itself. So you can see here the schema. This will be the schema in a kind of, in a string format. If you, kind of looked at it that way, use name, type. If you have looked at, if you kind of created Spark schemas, some of these things, may be familiar to you in creating like a struct type. But if not, you can see just kind of for one row, you have the field name, the field type, if it's nullable or not, and any other metadata. And then some sample data down below, you can see this as well. So that's just kind of, one way of looking at the transaction log. There are certainly better ways to do that, which we'll get into in a second, but just good to kind of see what's there, understand kind of what types of things are written. And then, so now we have our data in storage. I'm writing this all on a storage account that I have, and avoiding DBFS. Just I think that, it's not always the best practice. DBFS can go away, but, for the demo purpose, we could really do either. But, we have the data there. We can create it. We can read it with, the standard Spark reader. I'm always partial to PySpark, so that's what kind of makes sense to me. That's what I'm used to. Or we can also kind of create a table in the Metastore and then query this table, with SQL. I know a lot of people are more comfortable with that. So having those tables there does make that easy to, kind of consume and have, instead of, a long string of PySpark commands, a long string of SQL commands that, you can do a ton of operations on. You have the same functionality, but just kind of a different way of doing it. So I'll do it this way. I have a Python notebook, so I have to use the SQL magic command to make this cell just for SQL. I'm creating a table using Delta, and I, give the location of where my data has been written out to, which will register that in, and now we can, make queries against it. So instead of doing a read and display, we can just do, select star and limit that. We see the same data of what's there. You can also do this, if you want to, query this and then do some other processing further in Python. You can use spark.sql and write the SQL query, and then you end up back in the same thing where you have a data frame that you kind of work with in PySpark. So this is just another kind of standard Python cell that you can work with the data in that way as well. But otherwise, same thing. So I showed you the one transaction log. In this, I can describe the history as well. Might be a bit easier to read. So we can see the history here. It's the first version, the timestamp and user, the operation that was there, and just kind of the parameters of there. What was done. It was partitioned by the date, notebooks, and some operations on the file. So it read out 120 files across, I guess, 30 partitions for each day in November. Total bytes, total output rows. So we're just about 300 81,000 rows in that. So that's, we kind of have the first month settled. That's just kind of gives us a start to work into. We now can, do other things additionally to the data. So I want to start with just kind of adding in data. So to start this, I'm just kind of pulling from the second month that we have. In this, you started out with November of 2013. Now we're going to December of 2013. The same thing, just loading this, adding the column for partitioning. We can check that the dates are, within what we'd expect, which they are. Last pickup, the second before New Year's, the first pickup, midnight on the first. So you can see that this is the right data, and now we can just append this in. So it's basically the same write statement as we saw before. I've just changed the mode to append instead of overwrite. If we overwrite, it'll overwrite the table, but this will just add data in. I didn't specify the partitioning here, but if you look at this, after we write this out, since the scheme is already set up, has the column there, everything, the same thing will be, the same scheme will be applied down to this data where, we can see that, and we'll see, partitions for December as well. It'll work in the way we expect. So you can be explicit, but also if you kind of, forget that off, it's not gonna be the end of the world. It's gonna be smart enough to correct for some of those things. So we have this data written. This is automatically gonna be reflected in any new queries of the table. There's no, refresh table. There's nothing like that that you'd have to do on this. Everything's just there, and it's good. So you can, kind of automatically check this, and each query will go against the most recent version of the data if we specify, unless we specify something different. But we just check. Let's look at the count of daily rides. We can see that. This now goes up. There's 61 rows. It goes up through December 31st. So everything's been written in as you would expect. And the data kind of looks, pretty standard. So we can check out the history again, kind of going back to this. I'll go back to this a few times, where we can now see another version of this. Now we have version 1, where it's appended. There's no partitioning just because it's, I forgot to specify that. But otherwise, the same details built off version 0. That was version red, and these are the output files from the operation. So we wrote another 124 files with 600,000, an additional 600,000 rows. So you can see those. We can see kind of just track what's there. Making sure our operations we're doing kind of what we expected. So in this second data, there is some kind of bad data. There's some of the tip amounts, which is one of the columns in there, are pretty high. If you look at the distribution of tip amounts, lots of zeros, which isn't great. Kind of what you'd expect to see around the tip amounts, that type of distribution there. But you see some, it's kind of a long tail. If you look at this one, there's a number of tips that are $100,000, which seems a little high. So, if we're doing this in kind of our standard, data engineering, data cleaning pipeline, we might look at this and say, hey, well, that doesn't make a lot of sense. I think this data is bad. So if I'm, drawing any conclusions on this, I'm going to want to correct this data. So to correct this data, I just want to find the rows where, it's got that bad tip amount and come up with some rule for a new one. So we can find the data by querying everything from this, where the tip amount is 100,000. So you could put this here, you can put this in the SQL query, it'll get evaluated to the same, underlying plan. And then we're just kind of updating their tip amount column. So for this row, for this data, the tip amount is previously 100,000. Instead of this, let's just, make it the total cost, the fair amount, the extra, the tax, tolls, times 20%, and we'll round it up to 2 cents. So just kind of a, standard rule for the tips. We could, pick any percent. I just kind of picked this arbitrarily, and then this should, kind of allow us to, create we now have this data that we want to fix with the updated tips, and we want to be able to merge this back into the existing data. So the we have our kind of table in SQL, the green text data, and we just want to merge this back in on whatever kind of keys make it unique and update the records when there's a match. So if there's a match between these two things, we'll do this. So to start this, I have this table in that I've been working with kind of in the Python interface. I'm just registering this as a new table, kind of temp view that the SQL interface can use when I run these magic commands. I have to register it so it knows what to look for. But to do this, I'm merging into green taxi, which is my table that I created from the Delta on this, using the fixed data, which is my temp table. So that's the new data that I want to look at. And then here is my nightmare of a join condition. When I picked the data set for this, I didn't plan ahead enough to think of something that would have a good unique key. So I had to find out what makes this unique at that level. But in any data, if you find the kind of condition that would be able to uniquely identify a row, we can now look at that and say, okay, if all these conditions are matched, then we can do some operations. So in our case, when matched, then we're updating and we're setting the current data's tip amount to equal the fixed data's tip amount. We can do this way. If there's other data to insert, we could do a when not matched if there's some operations there. But we're just updating these few rows, so that's all we have to do. So in this, we can go back. I didn't run this, so that's why there's nothing new in the history. This may take a minute. So it's going to look for it's running this merge. It'll look for the files where it'll merge this. This might take a little while. It's got to rewrite a lot of files. The merges are not, or the errors are all kind of distributed throughout the data. So if the error, it's partitioned. If the errors all happened on one day, then it would kind of be able to prune down and say, okay, well, the errors all happened on this. We only need to rewrite that, but that's not run. So in this now we can see the different operation. We have this additional version. This operation was done by a merge, and in this we can see the parameters there. So this is how we matched the data. This is the action. This is what happened when there's if there was no match, which we didn't do anything there. So in this, we can also just kind of go over and look at what was done. No rows inserted because there is nothing new. We updated 30,000 rows. That's the number of rows that were in the kind of bad data set, and the total number of output rows, which is the same as before. So this just kind of gives us details on that update that we performed. We can see that everything worked largely as we'd expected to. And how we're doing it. So if someone wanted to go back and check it out, they'd be able to go and see this history of, okay, this is what happened, this is how it was done, and kind of go from there. We can kind of recheck the data, get that same distribution, and check that there's nothing out that high. There's one tip for $227, but we'll just leave that for now. There's a few weird ones here and there. So the data, now we can just querying this data again, back on the updated version where the data is corrected, and we're good from there. So that those few operations have taken in 2 months of data from 2013. Skip ahead a bit to data in 2019. At some point in the 6 years between this, the schemas updated for this data. So instead of having the pick up, drop off latitude and longitudes in the 2019 data, if we print the schema here, we can see that in this one there's a pickup location ID and a drop off location ID. So they've changed the way they record the kind of distance there. I think there's also a few additional fees down here they've added, some more taxes, fees, surcharges onto the fare that did not exist in 2013. So the data is a little bit different from before. So, we can go in here and we can try and, just write it in. But as you can see, and kind of one of the features that Delta gives us to, put some guardrails on our workflows is right off it fails, saying that there's a schema mismatch when writing to the Delta table. So that's something that we know, we know that's changed. So if this kind of happened without our knowing, our workflow would fail, and we'd be able to go and look at it and say, okay, what's the one that changed? But we had a schema mismatch, and if this is okay, we can either fix it, or if we're okay with this, we can use the option to merge the schema. There's a configuration where you can do it automatically. That might get a little risky if you think you've got all the edge cases, but there could be something else that you don't want in there. So we'll leave that the Spark configuration there, but go with this option there. Just on this one, for the sake of this, we're not too concerned about the schema on here. So we can just use the option to merge the schemas. And that kind of will override that, and it'll allow us to write the data in. And what will happen is, for the 2019 data, for the 2013 and 2019 data, when the schemas do match, the columns match, they'll just kind of append those together. But for the new columns in 2019, those will be added on to the end of the data set. So we'll now essentially just have those on the right of the data set. And those columns will be filled for 2019, and they'll be null for all the 2013, everything before where those columns didn't exist. And the columns that existed in 2013 that no longer exist now will still have values for 2013 data, but they'll just be nulls for 2019. So you can print out the schema, and you can see that that's happening. Now this has the same lat longs we've always seen, but if you scroll down to the bottom of the schema, you can see previously the pickup date was the farthest right column. Now we have these additional ones that were added. So the location, the drop-off, location IDs were added, and these are the two additional charges: an improvement surcharge, a congestion surcharge, that they're added on there. So these are the new things that we put into there. We can go back to our favorite history thing and see what's there. We have another write back to just kind of appending the data, and same notebook and cluster details, and same details on the number of rows and number of files written in that. So this kind of can take us through a number of the common use cases in writing to a Delta table. So now we have a Delta table, we've written to it, everything is we've kind of got the creation of the data, but now we might want to, optimize it a bit. So we have a number of, operations that have been performed, writes, reads, and if we want to kind of come and take that and say, okay, let's clean it up. Let's, a lot of this stuff can be done automatically with Spark configurations, but if you have a streaming job, it may, write a lot of small files, or if you have, some other things, and you might just kind of get, kind of a long history. So Databricks is given the optimize command, which will kind of take these files, it'll compress them into, kind of more optimally sized files. So if you have a lot of small files, it will compress them down into, one file that's, a couple hundred megabytes. I think they kind of standard recommend, you want your files between, 100 and 100 megabytes and a gigabyte. So doing this will just kind of, make that, do that operation for you. It will kind of, put those all together. And so when you query your data, that performance will be improved. Second thing they have is, Z order clause. So this will, kind of take that a step further, and kind of co-locate your data. So if you, if you have data where it's partitioned by, it will, obviously the data for within the partitions is similar, but this could take it a step further and say, okay, this isn't a good key for partitioning. It might over partition, it might under partition, but within that we still may be querying by this data. So I've picked this Z order of the pickup date time, so I still may query by the fine grained date time there. So by z-ordering this, it will the operation will co-locate similar data, so it'll just kind of put that all in order, and then when the stats are collected on the files, it can help the queries when someone reads the data. If they query on this, the Databricks can read those collected stats, it can read that metadata, and it can help speed up the data. It'll make it so you only read the exact specific files that you need. So you can run this and it will kind of put all these files together. And of course, my favorite operation, this will be tracked back in the history to see what details were changed as kind of part of this operation. Just a few seconds. So we can see this. We can see the operations here. We can also, I printed out the history there, the metrics here. So it added 67 files. It removed 262. So that's just done by kind of rewriting, shuffling around the data. The partitions that have been updated as well, and the kind of what was looking there, what was skipped. So we can see that there. We can also see, in this operation as well, the optimize, we get, similar with the merge, we get the details on what it was, what we were doing. You can do this on a number of conditions. You can optimize certain portions. You can leave other things there. This just did everything because it's, a bit more, but you do have more control for this. And then, same details that we saw above on what the files are there. So after this, we can look at, go back to one of these individual partitions. So if you look at these files, I think there's 5 files now. And you'll see here, if you look along the sizes, this is a relatively small file. This file is actually a bit bigger, smaller file and smaller file. So what's happened here is those 4 small files are what was originally written out in the original write. So this was the first write we did. It wrote those data out into the 4 partitions. So those are the original files that these that are no longer active. If you were to query this, we'd only go against the new file, this bigger file that's just kind of the sum of all 4. These 4 files have been now combined into one, but we still have these original files. So it keeps, this is part of the history that it keeps, where we can go back and look through the earlier versions of the file. If we only had the new version, it would query against that. But if we wanted to check something in the past, we'd want to go back to the data at that state. So this is, the older history of those files. So, we can go back and query these original, data sets, in SQL by giving just kind of a version as of. So you can do it by the version, and all the histories it wrote out with a version number. You can also do a timestamp if you want to do it that way as well. Let's do the version because it's a bit simpler. So I'm just going back to querying the data as it was in the first version. So you can see if we look at the min and max time, the first data we wrote out was just November, and you can see that reflected here as well, where it's November 1st to November 30th. We could do the same thing with the second version. We'd see November 1st to December 31st. So you can go back and query those different versions as well. And this is because we still have that transaction log and we still have that history. So, as you go through here, this is just a few operations, but if you have this in a production process, you may end up with a number of different versions and, kind of a long history of files that is, it exists and it's there, but you just might not have any, reason to go back to this. One of the things that if you, kind of see that, a lot of what Databricks will talk about is, if you have some compliance things where you want to get rid of data for a certain time, you might want to get rid of older versions of the data just for this. They use the GDPR example where, some user says, I want to, I'm requesting the deletion of my information. So you go into your data and you delete your delete someone's information out of the current version of the table, but since it's tracking the history, that information does still exist in a previous version of that file. So you might want to clean up some of this and delete some of this older data. So you can do this with the vacuum command. The vacuum will, get rid of any files and, kind of, data that's older than a certain period. So you can give it a retention period. The retention period default, I think, is 128 hours, which is a week. In this one, I've set it for 0. In the kind of default here, if you do something 0, that'll take you to only the current version. So they're giving you some guardrails on this, so you don't kind of delete something that recently. 168, that's what a week is. So it'll give you some guardrails there. They do this because this will kind of kill all ability to go back to previous versions, which may be your use case and may not be. If it is your use case, you can get around it by kind of disabling this check, which they've given here. This kind of will perform that operation that previously failed just after I changed the configuration. I probably wouldn't do this in a normal use case, but for the sake of this, you can see that, it'll delete. You can see the details it'll give here. It's finding all the old files that we don't need. It's going to delete those, clean everything out. And we can see the history as well. So now we see this, these details for the vacuum. It was completed, so the files should be gone and removed. There's some details on this. I deleted 386 files over 106 directories. So that's now cleaned up. And if we were to go back to check a previous version, let's say we want to go back to version 3, which is where we had the schema change, we're going to get an error because that data is now gone. We've deleted out the data that would be this. Spark's looking for these different files that were relevant when we had that version of the data, but that's now gone. So there's nothing more we can do about that. So the vacuum is going to be irreversible here on this, and we can check this as well. Previously when we looked at this, we had 5 files, 4 inactive and 1 active. Now we just have the active one as well. So that's kind of how, if you want to clean up some of these old things, get rid of data for your compliance, it has that ability to just kind of delete some of this out, so you can make sure your process is clean and manageable, and you're not keeping stuff longer than you necessarily want to be keeping it. So that's the end of my demo. This is a quick run through. Just kind of touching the surface on a lot of this. There's a ton of depth in here on kind of what's there. I have these links here. Project Home, Databricks space. There's a Slack community as well. See what people are asking. There's lots of discussions. How think people looking for assistance there. So if you're interested, you can join and get involved and see what's there and kind of be part of that community and get help yourself. And then just the Databricks documentation as well. So there's a question in the chat about the demo file. I'll have to look at the way that we would do that. These files are, safe to send out. This is all, kind of random public data. But I'll just have, I'll have to check into the mechanism for that. But yeah, that thanks for joining. Thanks for listening in. And yeah, thanks.
All right. All right, Patrick, thank you so much for coming in and hosting. It looks like you might have one more. Oh, you might have answered that. You might have one more question in here. Nope, I think you got them all. Okay. Well, yes, I know someone asked if the recording will be shared. Yes, the recording will be available tomorrow around noon Eastern Standard Time, and you guys will receive an email in your email box. So just look out for that. Like I said before, you guys, please feel free to reach out if you guys have any questions. Thank you guys so much. Please feel free to follow us on our social media channels. I will put that back up here for you guys so you guys can see that too as well. Please feel free to follow us on our social media channels. And if you guys don't have any other questions, thank you guys so much for joining. And Patrick, thank you so much for hosting. We greatly appreciate it.
Sure thing. Thanks everyone for joining. Have a good rest of the day.
Thank you. You guys have a good, wonderful Tuesday. Thank you so much.